Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. Hi, Chris.
Hi, Jesse. How are you doing?
Hey, I would like a little more enthusiasm when you say hi to me. What's up with that?
I don't know.
Man?
I'm not feeling it right now. I can't. I'm not an actor, Jesse.
I had Cranky Chris this morning, and I thought you'd sorted it out and become Chipper Chris, but I guess not. Cranky Chris is making
I'm not
back.
quite. I know. I'm mourning right now. So
you're in mourning, yeah.
I am in mourning. Right. Yep. But this helps to get to talk about the Grand Canyon is helpful to lift me out.
Well, that's what I was gonna say. I mean, come on, if this doesn't lift your mood, I don't know what will, man.
That's right. So, Jesse, let's should we just jump right in, start talking about?
Well, let me give a little bit of a backstory, real quick here. This is going to be the 30,000-foot view, the hot air balloon ride, if you will, with a fast forward button, directed and hosted by Chris Pulheis. He's going to be up there with a little microphone, telling us what's going on. But this is the overview of the geology of Grand Canyon. Really, National Park is what we're going to focus on. The rocks there. You can find we have 10, 12 chapters in our visual podcast series on this with images like what we're showing right here with this kind of custom images, custom GIFs that really dive into some of the details on the geology of the Grand Canyon, different rock units, different geological events, how the canyon was cut, for instance, things like this that you can find on our CampGeo mobile app. So click on that first link in your show notes. You can get visual podcast series there on the geology of the Grand Canyon. The other thing to note is if you have questions, please leave us a comment. If you have questions, thoughts, reactions, some things you like, some things you didn't like, please leave us a comment or shoot us an email, planetgeocast@gmail.com. You can also follow our podcast in any podcasts app that you have. Just search Planet Geocast. There's some links in the show notes to that too. So with that, Chris, the geology of the Grand Canyon. This is really the basics of geology. What you teach basically advanced placement geology in high school. I teach the same class at college level at Penn State. I always talk about I describe them as very intuitive and simple rules of geology, but they're hard to figure out on your own. Like once they're pointed out to you, then they're easy. They're dead simple, cross-cutting relationships, pretty easy. But people don't stumble upon these rules and relationships on their own. And the Grand Canyon is just full of first principles geology. It just slaps you in the face. It's like right there for you to see and understand.
100%. It absolutely is. I like to think of, when I look at the Grand Canyon, to think about it as though it's a book. And the layers that we see with the Grand Canyon are the pages of the book. The thing is, and we get into this, in our book in a lot of detail, actually, in our visual podcast series, there are many, many, many missing pages of the book. Pages have been ripped out. So we have this book, what we see, it's mostly missing, actually. So we have much missing time here. So we can think about it as a book, but just remember that a lot of the pages have been torn out. In fact, entire chapters have been torn out of the book.
Yes, exactly. And it's a really, the question you might be asking yourself, you should be asking yourself, is why? Why did these pages get ripped out, or what does that represent? And it's just missing rocks. We're missing time here. We don't have all of the rock record at our disposal all the time. And so, it gets complicated in there, and because we don't
surprisingly
have that record. Yeah, exactly.
Because you look at the Grand Canyon, and what's laid out before you is kind of straightforward. You can see some angularity to the rocks, and then the rocks on top of that are all flat. And geologically, it looks kind of simple, but in reality, it's not, because erosion is a gigantic eraser. And it just wipes out, it wipes out these layers and they're gone. And so we're going to talk a little bit about that. But like I said, too, we do get into much more of the detail, and we get into the weeds in our visual podcast series. But this is just a 30,000-foot overview, general geologic sketch of the Grand Canyon.
That's right. So, and what we're going to work through, we're going to work bottom to top, because the beauty of, and this is one of the first principles of geology, when we're dealing with sediments, flat-lying sediments, the oldest stuff, and I think this is intuitive, the oldest stuff is on the bottom. So the oldest stuff in the Grand Canyon, the oldest rocks, the oldest record, the first pages of the book are down in the bottom. And in many places, you can't see to the bottom from the rim of the canyon, but you like can't see the Colorado River that well. But we kind of have an upper canyon and a lower canyon, and the lower canyon shows and contains the really rough, altered, what we call crystalline basement gneiss story, which is the old rocks at the bottom. And so this first image actually doesn't show those very well because they're really far down in the canyon, in the lower part of the canyon, near the Colorado River. That's where the old stuff is. And so that's part of the story and part of the geologic record, but I don't know, it's harder because you can't see that, right?
Right. So yeah, let's get down into that inner gorge and let's talk about those old basement rocks that you just alluded to. So this story really begins 2.5 billion years ago. The record of the first two, the previous 2.5 plus or 3 billion years, we can't talk about it because those rocks just aren't here. So we're
exactly
zipping through all that.
We're gonna move through. Chris, I'm just gonna point out this cross section. We're looking. This is the lower canyon. This bottom left part of this little schematic cross section we're looking at. This is the Vishnu schist down here. The Zoroaster granite. These are the two rocks we're talking about. And then the Grand Canyon supergroup a little bit we'll touch on, but these are the really old stuff down here. This is the stuff I love. It's garnet studded schist. Chris, I took in undergrad. We went to a field trip class that we went to the Grand Canyon, and it was mostly about the geology of the Grand Canyon, about that region, and we all made shirts that said "to the Vishnu" because we wanted to hike down and get to where we could put our fingers on the Vishnu schist down there. And so we all had shirts that were like Hope College geology trip, whatever, some year that I won't name, and it was to the Vishnu.
Did you guys go down?
Yeah, we got to a point where we didn't get like super far down, but we could see it and look at it, and
all right,
got close. So yeah.
Were you able to touch it? Were you able to touch the contact? What we
no,
call
we didn't make it down. You're part of a big group. We unfortunately didn't make it down to touch the contact.
Okay.
We have a ton of missing time, but
you could see it.
You could see it. Yeah, we didn't get to touch the great unconformity, but we could see it. Yep.
All right, so we're talking 2.5 billion years ago to 1.8. So a span of about 700 million years is the beginning of the story of the Grand Canyon. And basically it began as a sea, deposition of rocks like shales, sandstones, and limestones, where we had this, the sea was transgressing and regressing. It was coming and going. That's how this story begins. These are the parent rocks of what would become the Vishnu rocks, your shirts of "to the Vishnus." So
that's right.
Yeah, that's how the story begins, as actually these intensely metamorphosed rocks, schists and gneisses and so on, were actually sedimentary, deposited in kind of a boring, if you will, story of just shallow marine deposition. What happened to them, Jesse?
Well, they got metamorphosed into a large mountain building event, 1.9 billion years ago. They got metamorphosed. These sediments got swept up into a large, probably some sort of plate collision event. They got buried pretty deep, and we can tell how deep because we can look at minerals like garnet in the sediments. That garnet is a metamorphic mineral that grew in the sedimentary rock as it was being metamorphosed, and is a metamorphic mineral, and it tracks those processes. So we're really watching kind of multiple collisional events, and I'll skip ahead in the images here to kind of one example of this would be basically island arcs colliding with the existing continent. So if you have a Japan-like thing out in the Pacific Ocean and it's being brought along by a subduction zone system, it's kind of following along, and then it smashes into the continent, what's going to happen is that thing's going to just get slammed onto the margin. The continent's going to grow, but it's going to grow in a tortured fashion. A lot of the edges of the sediments that are caught up in that, the rocks on the edge of the continent are going to get deformed and altered and ultimately melted. And that's the process, because they're under so much heat and pressure, they get melted. And so then we have granite forming, and we metamorphose the rocks, and that's what's represented in the Vishnu and the Zoroaster granite down in the bottom of the canyon there.
Yeah, so it's kind of shocking we're starting the story with actually talking about really impressive muscular mountains that form. That's the beginning of the story of the Grand Canyon. And obviously it doesn't look like that today. Those mountains they were formed. These are really, really deep rocks. They got brought to the surface. They got eroded flat. So we had this mountain building event formed them. And then through weathering and erosion and isostic adjustment, they got brought to the surface. Then they were eroded flat again. And so that's kind of where we're at.
So the eroding flat part, Chris, this is another first principle of geology that is sort of so beautifully represented in the Grand Canyon, is that you have to think, how did we get rocks that were buried really deep such that garnet grew in them, such that they melted and we formed this Zoroaster granite? That granite was a magma. It crystallized in the earth very slowly, grew big grains. It was deep in the earth. We're talking kilometers or miles, many miles deep in the earth. How did that thing get up to the surface such that sediment is deposited on top of it? That means that it was right at the surface. It was underwater. It was cool. Sediment was laid down right on top of it, what we call an unconformity. How does that happen? And Chris, I've stolen this analogy from you because I've learned a lot of my analogies from you. You ready for the particular one I've stolen? Maybe you've come up with a new one since I've stolen this from you. So I'll be interested to hear if you've got a newer analogy. But the cargo ship here. So if we have imagine a big cargo ship with cargo tanks stacked really high on this thing. It pulls into port. That ship is sunk really, it's deep draft. It's sunk really down far low. As the top layers of the shipping containers get pulled off the ship, the bottom, the keel, starts to float up a little bit. In those bottom containers, the bottom layer of containers, while those were kind of right at the ocean level probably before, they start to float up a little bit higher. And as you take off another layer, it floats up higher. Take off another layer, it floats up higher still. This is the process that continents go through, which is called isostatic adjustment. If you take off the top of the mountain, the bottom of the mountain will kind of float up. And this GIF here shows that really well. We've got deep metamorphism happening. These yellow or these orange blobs are granites, and those eventually get exposed at the surface. So Chris, two questions for you. First, is that a good analogy, and or do you have a more recent one?
I think it's a good analogy because it's mine. It's the one that I use a lot. I still do use it. I would just say that, the bottom layer of the containers on that ship, those represent the Vishnu schist and the Zoroaster granite. Those are the really, really old and deeply formed and seeded rocks. And as you strip away the layers on top of it, those basement layers get closer and closer and closer to the surface, and eventually they're at the surface. And we know that this happened. This had to have been the only way because of what's directly on top of these rocks. These rocks are tortured.
Chris, before you get to that real quick, I'm going to ask you a leading question here, because we're talking about not just taking off, containers from a shipping container, but scraping the tops of mountains off, kilometers of mountain gone. How does that happen? What does that look like, and how does that happen? We're talking about a time span of the better part of 300 million years. That's a lot of time where weathering, erosion happened. And so what that does is it removes the mass that makes the tops of the mountains, and that gets brought down to the valley floors, and then it gets removed by rivers. It gets carried away. So when you remove that amount of mass, then the mantle pushes back up on it to achieve a new gravitational balance. So you have this kind of pattern of weathering, erosion, and then episodic uplift. And that's that isostatic adjustment that you were talking about there. So that's how this happens. And it would be really cool to watch and fast forward. Really quick analogy here, Chris, or to kind of make this relevant. Compare the Himalayas or the Rocky Mountains to the Appalachians in the western United States, or in the eastern United States. The Appalachians, where I'm right now, we have deep rocks exposed at and near the surface, and especially if you go to the eastern seaboard, eastern Pennsylvania, Delaware, New Jersey, Maryland, if you just go down underneath, you're going to hit really, really high temperature, deeply metamorphosed rocks that have sediment sitting right on top of them. That's an old mountain building event. That's an old mountain range. That's many hundreds of millions of years old, and we still have mountains there from this process. Just erosion has scraped away the top layer. So that's the kind of juxtaposition. Think of the Himalayas or the Rockies, compare those to the Appalachians, and that's the process we're talking about.
So all right. So we had these muscular mountains forming. They get eroded. They're getting older, and they're getting flabbier, if you will. They're not young and muscular anymore. And so about 800 million years ago, then the next event that took place was another tectonic event that happened. And Jesse, what's this look like? This, 800. So this is still Pre-Cambrian. This is still old stuff. What did this mountain building look like? It's completely different than the first one.
Yeah, we can get mountains formed, as you've mentioned before, and I think you touched on this really well in the Tetons video. We can get mountains by extension as well, by stretching apart and forming mountains by actually pulling the crust apart, where some blocks of crust drop down and some are kind of thrust up. The Tetons is a great example of this, where we get normal faulting, we get huge mountain ranges because of that. And so this is one process by which we can get this. So we get horsts and grabens, this period of erosion and weathering these things down, and we get some snowball earth events, and we finally get these things, these rocks that were deeply metamorphosed, the Vishnu schist, the Zoroaster granite, we get them exposed at the surface finally.
All right, so Jesse, we have this, this isostacy that was happening where the mountains were being eroded and uplifted and eroded and uplifted, but then, so we take these mountains and we basically bring them back down to sea level, but now these old deep-rooted rocks are exposed at the surface and relatively flat. Then we have this, you get these patterns in geology. When you have mountain building, then weather and erosion happens. And after weather and erosion has done its thing, then deposition returns again. And that's exactly what happened. So a sea returned to the area and deposited the supergroup near the bottom of the Grand Canyon.
Real quick, this is like the last frame in this GIF here is showing, the sea invades, and when sea invades, we get deposition. There's sediment being deposited on the seafloor. That's what's happening. And we're forming the Grand Canyon supergroup. So I'll skip back to this image. We're talking about these purple rocks here, which are not exposed everywhere, but in many cases they are exposed. These are tilted now. And the tilting is what we're referring to, that extensional event, this sort of extensional mountain building event, to get these rocks tilted. And we have a whole chapter on this in our visual podcast series on the supergroup and this kind of event, and some cool GIFs and some cool images that show it. But I think we could kind of skip past this, Chris, move relatively quickly through this. Is that okay to kind of move past the supergroup? Have we done it enough justice for now? For this intro?
Yeah, I think so. Absolutely. Yep. Let's skip to the next sequence of rocks that
we have to get to the big dog. I mean, the sequence of rocks that's represented by this last stage, which is a huge amount of rocks that you can see from the rim. If you're standing there at the rim of the Grand Canyon, these are the rocks that dominate your view. All of the rocks in here that are called the Phanerozoic strata that form after this tilting event, and they start to form. There's a bit of debate about how this happened, but we basically scrape the continent flat again, and we start to lay down flat-lying sediments on top of it, what's called the Great Unconformity. It's an event that's exposed in many parts of the world, frankly, but is kind of defined in the western United States here, in the Grand Canyon area in the western United States, where you have these metamorphosed rocks below and then flat-lying sediments on top of it. All over the western United States, you can see this, called the Great Unconformity. And so I think, Chris, we have to go back to this image of transgression regression to help explain this, right? How do you walk students through this? Because I find this topic, this intro to geology theme or fundamentally important process is kind of difficult for students to grasp.
It is. So, I mean, you're right, 100%. It is a difficult concept. So I call it shifting seas, transgressing, regressing, shifting shorelines. But the thing is that you get a sequence of rocks. Typically, right at the shoreline is where you're going to get sandstone deposited. And then in calmer waters, deeper, further away from the shoreline, you're going to get shales. And then a little bit deeper yet, still shallow marine, but deeper, you're going to get limestones deposited. And so you get this sequence of rocks. Well, the thing is that when sea level rises, that sequence shifts with it. It follows the shoreline. So these rocks are, as the shorelines kind of go back and forth, they come and go, they're transgressing and regressing, the rocks go with it. And so what happens then is you get this stacking of rocks on top of each other, where I have sandstone, let's say at the bottom, and then shale on top of it. That represents a transgressing sea, because that shale was deposited in deeper water. And then you can have the shale and then back to sandstone on top of the shale. That means sea level fell, it regressed. And so it's just basically this GIF shows the shoreline shifting and the rocks shifting along with it.
That's right, Chris. And I think the one thing to remember here is that we're talking about time as a vertical phenomenon now. So you have to remember that sediments get compacted and basins subside. So you don't just dump a bunch of sediment on and then that doesn't stay there. That kind of sinks down over time. The sediment gets subsided and the basin subsides. There's more room for more sediment. And I use this example, Chris. I teach in this big lecture hall, 250 student seat lecture hall that is like an auditorium. It has, the hallway. You walk in the door, you're up high, and you walk down toward the front of the podium. So when I'm lecturing, I'm down low, and the students are up in this auditorium above me. And so I would say, okay, let's imagine the sea level is at the door height. So me at the podium, I'm in the deep water. People right in the front row, they're in the deep water with me. People up by the door, the students who are sitting in the back sleeping, they're up right near sea level, right near the shoreline, right? And so you say, okay, are you up there by the door? You're getting sand because you're in this wavy environment. The people in between, you're getting shale. The people down by me in the front row are getting limestone. Now, what happens if I increase sea level and the sea level goes all the way to the ceiling? And, then we'd have to blow back the doors and the beach would be, way far outside of the classroom. And then say, okay, now what sediment is being deposited on top of you? Okay, do that exercise drop sea level? How does that change the sediment that's being deposited in your seat? And that's what I think the key is like, remember, we're looking at a single point in place and we're going vertical, and vertical is time here. So we're changing sea level through time in one location, which kind of the last image of this GIF, the last few images kind of try and represent. We're looking at this vertically. So
the net effect is I want to, real quick, Jess, we got to go back to the extensional event and then what happened after that. So you had these horst and grabens that were forming, mountain building event again. And then after this event, after the sea deposited the Grand Canyon supergroup, then the tilting happened through this extensional event that did this. Then we have to erase a lot of rocks.
Yeah.
Yeah. In between the Grand Canyon supergroup and the Paleozoic strata that we're talking about now, we ripped out a lot of pages. A lot of that rock is gone, and we're going to form what's called the Great Unconformity then. We're going to start deposition.
Can you just put a pin in that and let's come back to that? Let's end with that discussion about missing time a little bit, because we have a couple images coming up that are really good at emphasizing that point. Let's just walk through the flat-lying sediments here, and this is as I said, this takes up a huge amount of your viewpoint. If you're on the rim looking at the Grand Canyon, most of the rocks you're seeing are flat-lying Phanerozoic sediments, and there's a whole bunch of different rocks in here. I think, Chris, I'm curious. I want to ask you what the most important point to you about this is. For me, the most important thing to note is that limestone and sandstone form cliffs. Shale forms the slopes in here, and that, for me, that's the most important point. I'm curious, is that what you think too?
Yeah, absolutely. It's geology at 75 miles an hour. I like to call it that in my class. Like, we don't have to stop the vehicle. We can drive past the Grand Canyon and I can point out the window and say, all right, what kind of rock is that right there? And we're looking at whether it's a slope forming rock or a cliff forming rock. And if it is a slope forming rock, we don't have to get out and take a bite of it to confirm that it's shale. We know it's soft and weak and wimpy because it's not strong enough to form cliffs. So
because it weathers that way, right? Yeah, exactly. The other important point here to note is that this is shifting shorelines. And in this time period, sometimes we see really nice continuous shifting shorelines. I'll go back to this GIF. Sometimes we have this nice continuous record of, limestone, then sandstone, or limestone, then shale, then sandstone, then shale, etc. And sometimes sea level drops such that we get an unconformity and that there's missing time again. So this is not a continuous record. And some of these bold lines that we have in here are gaps in time again. So this is it looks really simple on the surface. It's actually really complicated because shifting shorelines are really it's a complicated process, and stuff gets erased still. And it's actually really hard to see when stuff gets erased, but it's there. So we've got shifting shorelines depositing a bunch of sediments for hundreds of millions of years. I think
that's right. Long time. We know that the sea came and went at least 8 times. And every time it went away for a while, that's where we had missing time. Pages are getting ripped out. Erosion happens when these rocks are exposed at the surface. So
that's right. That's
where we are. But the sea went away for the last time about 80 million years ago in this area. And that was brought upon by the very famous Western mountain building event called the Laramide Orogeny. So it began to affect this area, and this is it's a thickening of the crust. It was further west than where the Grand Canyon is right now, and it just drained the sea for the last and final time in this area.
Yeah, that's right. And there's a whole bunch of kind of interesting events to think about. How do you get these rocks that are forming down by sea level and get them exposed up high now on the Colorado Plateau? We had to form the Colorado Plateau. There's a bunch of different sort of regionally important events that are not necessarily trapped in the rock record in the Grand Canyon. But Chris, let's end with talking about a rock, and then we can move into the time and missing time thing. I think it's a really interesting story. These volcanoes, these little cinder cones that's represented in this schematic here, and I'll skip ahead a couple images here to show one example of these really cool things: lava flowing into the canyon and creating these lava dams and damming up the Colorado River and doing all this crazy stuff. I think this is just such a really cool story that'd be amazing to see from your hot air balloon with you.
Absolutely. Yeah. I mean, you can see some of these volcanoes that represent this material, right? That are not very far away from the Grand Canyon, that are easily accessible. I'm thinking like Sunset Crater. Have you ever been there? You ever been to Sunset?
Yep. Sunset's a beautiful one. Yep.
Yeah. And there are many of these kinds of volcanoes all over the area there that fed that was the source for these lava flows that we're looking at right here, that just kind of spilled down the canyon walls. And I mean, Jesse, that part of the story too would just be unbelievable to watch, because, when they get down to the bottom of the canyon, they dam the river up, and then the dams would break, and just the violence of this story is, really cool part of the story for sure.
These are like 725,000 years ago. There's the last eruption was about 100,000 years ago. So there's many kind of eruptive events in that time period. They're relatively, well, some of them are really big in the region, not in the Grand Canyon specifically, but some of these things are quite large. But many of them are small on the scale of this. I mean, huge to the human experience, but not geologically huge as we think of volcanic eruptions.
Yeah. So Jesse, can you put a timestamp on this kind of volcanism?
Yeah, 725 to 100,000 broadly. That's kind of the time period where we're talking about those. So I just mentioned
the last eruptions were about 100,000 years ago.
That's right. Hey, Chris, I think one thing here, maybe should I skip ahead to this timeline thing real quick and just show
let's talk about that.
This timeline but I want to talk about one thing on here, and this would be the great benefit of being in a hot air balloon ride. And one thing that just is astonishing to me is the fact that we don't really have a consensus view or a well-accepted view on how the Grand Canyon actually got cut. How and when did the Grand Canyon get cut? We've talked to people on our podcast about this. There's several different models for how this happens.
Yeah, it's kind of funny. You and I think each prefer a different model.
Yeah. As non-experts, reading, we've just read about it. We haven't really been, in this debate at all it's up for debate. There's like, I would say 4 different models for how this happens and how you actually cut the Grand Canyon, because there's some really, it's an interesting problem. And I think this is something that I think everybody should take away from this is like, we don't know how the Grand Canyon is probably one of the most famous physical features on the face of the earth. We don't know how it formed. There's a bunch of, some people would say they do, but there's no consensus view. There's no universally accepted idea. There's a bunch of models out there, and there's a lot of debate about how the Grand Canyon actually got cut, the canyon part.
Here's what we can all agree on. We have old rocks and we have a young canyon. You know, the canyon started forming, we think, about 5 million years ago. And geologically, that's very young. The problem is, Jesse, right? Why is there no consensus on this? And it all deals with the Colorado Plateau. You have this high area. Rivers don't tend to cut through high areas and carve, these spectacular V-shaped canyons. That's the dilemma, right? I mean, that's why this presents such a problem to geoscientists, because why would a river cut through this? Why would it do this?
And we have a whole chapter on this discussion, this debate, and point out some of the interesting thing. The Colorado River does this weird dog leg, and it cuts across the Kaibab Plateau. Like, rivers don't typically do that. Was there a massive lake involved in this process? Was it something to do with karst topography? Like, there's all sorts of interesting ideas, and I just think it's a really important thing to keep in mind that there's a lot about our planet we don't know, including how one of the more famous features on the earth was actually cut. And the problem is it's a cutting process. Like, cutting a canyon is a destructive process, so it's destroying the evidence for its own behavior and the way it formed, right? So this would be amazing to be in a hot air balloon watching how this happened and actually figure out, how did this amazing, spectacular canyon get cut over the course of millions of years?
I have a question for you, and I don't know if you'll know the answer to this. You and I have this discussion all the time where I rip on you. I'm like, because you're the doctor in the house, you come on, guys.
You rip on me?
Figure this out. You doctors.
I don't think you've ever ripped on me, have you?
Yeah. Okay. But here's my question, Jesse. And I've never asked you this before.
Okay. I'm getting, hold on. Let me get prepared.
Yeah. Okay. Yeah. You ready for this? So if the problem is the Colorado Plateau, why would the river cut through this? Why did this happen? Is it at all possible that the plateau formed after the canyon?
Well, the Colorado Plateau is probably unlikely. The Kaibab uplift area that kind of separates the upper reaches of the canyon, or the kind of upper reaches of the Colorado from the lower reaches, I think is. I don't think so. I mean, I think that most people would agree that this is a interesting problem because it cuts across that, and that thing was uplifted there. I mean, there's many ways, as we've talked about before. We had a great an interview and a couple discussions on our podcast about this process and how rivers cut across high topography. And one of them is exactly that. Like, rivers can cut across high topography if the topography forms after the river. And then, if there's a river system in place and you just kind of push up part of the crust in the middle of the river will just cut down through that if the uplift happens slow enough. So that's kind of what you're alluding to here. The Colorado Plateau, I think, is an older feature. The Kaibab uplift, maybe a bit younger. But again, this is not an area of deep expertise for me. So I don't exactly know I can't point you to data that proves that. If that makes sense.
Understood. Yep. Okay.
Now, hey, Jess, I could make something up that sounds close, maybe, but
no, you couldn't actually. I don't think you're that. You're not that clever, and you're not that quick.
That's true.
Hey, let's go. Can we go to that last image there?
Absolutely.
Where we talk about the missing time.
This is so cool.
So you told me to put a pin in it.
This is your baby. This image is such a cool one. I love this graphic. Yeah. Great.
Yeah, I mean, look at the book. We have a shell and with some pages in it, but most of the pages have been torn out.
It's amazing,
and
I think this
amazing. Drives it home, because this is a linear scale that we're talking about now. This is actually to scale.
And if anything, the amount of rocks preserved in the second image in that GIF, the stuff that's not grayed out, if anything, that's an overestimate, because it's really hard to fit all the unconformities in an image like this. like this is an overestimate of how many pages are left in the book. There's probably less than this.
Yes.
And it's
this at any one spot, right?
Yes,
that's what you're saying.
Yeah.
You can go to other places and we have those pages preserved, but yes, at any one spot, there's a lot less than what we see here for sure.
This, Chris, is what makes geology. Okay. I'm going to propose something here. See what you think. Get your thoughts. What's your take? This is what makes geologists great. Geologists as people, because this is hard. We're talking about three-dimensional processes that happened hundreds of millions, if not billions of years ago, where most of our pages are missing. That means that geology is fundamentally a different science than many other fields, STEM fields, really. And it gives us it gives geologists, people with a geology degree, a really unique worldview, I think, and sort of critical thinking skills of geoscientists are I don't want to offend anybody, but I'm going to, different than other fields of science in many ways, I think, because we deal with this problem. There's so much missing. There's so much we don't know. Astronomers probably have the same kind of thing, I think.
Was there a question embedded in there? I thought you were
What do you think about that?
Take on something.
What do you think about my hot take, Chris? No, I want your reaction to that.
You know this about me. I think, geoscientists look at things and problems differently. We do have a different take on the world, I think.
Yeah.
For sure.
Is this the reason?
Which I think is it's a skill set that is important. I think that's why you get a lot of geoscientists that ascend to careers that you would never imagine a geoscientist do. Why? How in the world did you land in this spot? Well, it's because we look at things a little bit differently than other people.
I mean, I've met geologists that are heads of venture capital firms, and the geologist is the head of DARPA, and geologists are in all sorts of places that are nonlinear career, trajectory paths, and many people go through that. It's not just geologists, but I think this is one thing that makes geology so interesting and a really powerful sort of critical thinking skill set. So we get to flex that muscle a lot when we're thinking about rocks because we don't have many pages. So you told me to put a pin in it a second, and I want to just come back to it because, I asked you if you got down to the Vishnu and the Zoroaster, and the reason I was asking that question is because, there's that great unconformity where you have this missing time between a lot of them actually. You have missing time between the Vishnu and the Zoroaster and the supergroup. And then you have a lot of missing time between the Paleozoic strata, what everybody sees when you look at the Grand Canyon, that lies unconformably on the supergroup and also in places touches the much older Zoroaster and Vishnu schist. And it's a famous thing to look at and to contemplate all that missing time. And I was just going to ask you because did you touch it? But you didn't get down there to do that. But I've touched the Great Unconformity in other places, not in the Grand Canyon, though. It is one of the, I don't know if it's the easiest to get down, beneath the Kaibab Plateau and actually get down to that level. It's a pretty big and potentially, especially in the heat, dangerous hike if you're not prepared for it. And a lot of people go in unprepared. But it is a spectacular place to see the Great Unconformity, which is just an amazing feature. You just have to imagine continents getting the tops scraped off of them and then new sediment being deposited right on top. Just a spectacular story, Chris. Spectacular place. And the Grand Canyon is an amazing place to learn the first principles of geology. The geological story is amazing. You can get more information, deeper discussions on our CampGeo mobile app. First link in the show notes. We also have a bunch of different podcast episodes that are on your favorite podcast platform. Just look at the Planet Geo podcast. And we'll have more information coming your way on the YouTube channel here too. So give us a like, a subscribe. Please comment if you have any questions, thoughts, suggestions, or send us an email, planetgeocast@gmail.com.
Cheers.
Peace.